Hey there, good morning, chemistry team. Let's continue along our intermolecular forces path, looking at specific types of them. So last video we did ion forces, right? So ion with ion. We did ion with a polar molecule, or ion dipole forces. And then we did an ion with a nonpolar molecule, so the ion-induced dipole, because it caused induction, distorted the electron cloud, made it from symmetric to asymmetric. Yay! So now let's focus today on let's take the ion out. So think of ion as like superpolar, right? So let's look at just a normal polar molecule. And that's where this term dipole comes from, because it has a permanent dipole moment, right? So if you've got a molecule that's asymmetric, so remember from last semester, you draw the Lewis structure, draw the Vesper structure, calculate the electronegativity difference between all the different atoms making up all the bonds, and does it have polar bonds? So if it's asymmetric and has polar bonds, so those bond dipole moments don't cancel out, they add together, you get an overall polar molecule, right, with the resulting dipole moment. Now, in my class, we're not going to be measuring those, right? So maybe if you take computational chemistry or PChem, something like that, you may actually calculate the strength of that dipole moment. I think they use Debye's or Debye's, right? And you can put numbers to that. I'm not going to in this class, but we can qualitatively say, hey, these are both polar molecules, but this is more polar than that one, right? It has a stronger dipole moment. So that term dipole, when we're talking intermolecular forces, means a molecule that has a permanent dipole moment, right? It is a polar molecule. Boom! Because of the asymmetric electron charge density distribution, right? So the electron clouds are distorted. We good? We good on our definition? Not going to review how to determine that, but these would be examples, right? We'll use these for some examples later. And just like we did with ions, let's put an ion with an ion with a polar molecule, and an ion with a nonpolar molecule. We'll do the same thing. We've already done the ions with polar molecules. So we'll take a polar molecule with a polar molecule. How do they interact? What kind of intermolecular forces happen? Whether they're the same species or two different species, doesn't matter. It's the same concept. And then we'll take a polar molecule with a nonpolar species and look at the induction that happens. Very similar with them. It gets easier and easier. It's almost the same thing as with the ion, right? So CH2Cl2, if you draw that, right? Let's do the Vesper structure for that. If you go through and do the Lewis structure and whatnot, you get that tetrahedron, right? You get the 4 bonds to the carbon, and you can put the hydrogens or chlorines anywhere. I like to put the chlorines together. You can rotate it all you want. So you can see, so let's put the chlorines here in the plane, and let's put the hydrogens outside of the plane like that. You can see the chlorines are way more electronegative. Always have a nice electronegativity table around with you. So you can see chlorine, yeah, it's about a 3.16. Hydrogen's a lot lower, 2.2. Carbon is a 2.58. So the difference between the carbon-hydrogen, 0.35, so we'd consider that a nonpolar bond, but the carbon-chlorine, that difference is greater than 0.4, depending on what your professor uses, right, to designate nonpolar bond to polar bond. But those chlorines are way more electronegative. So you get this buildup of negative charge on this side, right? It distorts that cloud, positive that side, and we just draw that arrow representing that permanent dipole moment. So this would represent CH2Cl2. So you can see that in 3 dimensions. The way I have it written, I have the 2 chlorines. Let's take a hydrogen. No, chlorine's up on top. So that's the way I drew it. So chlorine, carbon, chlorine. See a hydrogen coming out at your face. Boop, boop. That's the open wedge. Hydrogen coming at my face. That's the dashed wedge. But you can see how those 2 chlorines aren't opposite each other, right? So those polar bonds are enhancing each other, building up this region of electrons here that's higher than over here by the hydrogen. So it's partial positive here, partial negative on this side. Permanent dipole moment, right? We can do the same thing with PBr3. Take the phosphorus, right? That'll have a lone pair on it, so it still has that tetrahedral electron group geometry. But let's put the bromines here, and then that becomes a lone pair up on top. So that lone pair disrupts the symmetry. A little bit of review here. If you look at the phosphorus-bromine bonds, right? So take a look at phosphorus at a 2.19, and the bromines over here at 2.96. So that difference is greater than 0.4. So these are polar bonds, and if you look at this molecule, so let's say this is the phosphorus. Let's just call the blue as as bromine, even though it's actually the wrong color for the model set, but you get the point, right? So you see that's that asymmetric structure, right? So these polar bonds are pulling down this way. You're going to get a buildup of electrons down in that central region where these bromines are. So I'm going to draw the partial negative there. Boop. And you shish kebab it straight on through. It has that permanent dipole moment. So we'll take a look at what happens when you bring these together, or two molecules that are the same together and whatnot. And then water, of course, is your prototypical polar molecule. Got that bent structure. Also comes from a tetrahedral electron group geometry. But let's put the hydrogens in the same plane and put the lone pairs there. So if you want to erase that, you can erase the dash and wedge and just put the lone pairs where they would go. So water's pretty straightforward, right? It would be, we'll just take this as an example. Get rid of these chlorines. Boop. Those would be the lone pairs where those holes are. So that's what water, you can see the asymmetry here, right? So what happens is you get that oxygen is more electronegative than the hydrogens, and it's pulling electrons towards it. And you're building up, where'd my purple go? You're building up that negative charge over by the high oxygen. And in that central region between the hydrogens, you're losing electron density because it's getting pulled that direction. And you got that permanent dipole moment. Right? So that's what we mean by dipoles. So let's interact some of these things together and take a look at the specific types of intermolecular forces involved with the dipoles. All right, you ready? Let's look at the first of the specific intermolecular force type involving dipoles, and that'd be the traditional dipole-dipole forces. Two nonpolar molecules coming close together, right? Moving slow enough, maybe a low enough temperature where the short-range intermolecular forces can lock into place. Whether they're the same species or two different species, I just need two polar molecules that have permanent dipole moments because of the asymmetric cloud, electron cloud, right? So let's take our two CH2Cl2s, and we'll do it with the same species, and look at how this impact boiling points and all those kinds of things later. So we'll take CH2Cl2 and bring them close together and look at what happens. Maybe they're in the gas phase, and we're going to bring them together, and if it's cold enough, they're moving slow enough, those forces of attraction, those intermolecular forces, can lock into place, and that would liquefy it, right? Be condensation. Molecules in the gas phase, if it's cold enough, the intermolecular forces lock into place, and shoom, and you got, I don't know what it sounds like when gases come together to form a liquid, but it sounds good enough to me. So let's draw our two, we'll draw the specific molecules, and then we'll draw the generic little piece, rices with the partial negative and positive on there. Where's my black pen? So let's do a CH2Cl2 like we did before. So let's do the carbon, the chlorines. Oop, that would be the wedge and the dash. And these are three-dimensional molecules we're trying to draw on a two-dimensional surface, right? So this has that partial negative here, partial positive there. It's got that permanent dipole moment, right? Although we don't need to draw that dipole moment when we're doing this. Right? Just that we have a partial negative, partial positive, and that's permanent. And in the gas phase, that would be spinning around, rotating, and whatnot. Well, if that comes into, so that's moving around, say, in the gas phase, if it's too warm, they're just going to go whoosh, fly by, right? They're not going to notice each other, and you won't get condensation going on. But if it's cold enough, remember, intermolecular forces are impacted by temperature. If it's moving cold enough, it moves slower. And they're rotating, and if they rotate in such a way that the positive end of one comes near the negative of the other, boop, they lock into place. Now, that wouldn't happen. The two negative sides wouldn't come together, but if you get the positive side of one next to the negative of the other, they can lock into place, and that happens in 3 dimensions. You get your liquid. So let's get that other CH2Cl2, but let's rotate it around so the hydrogens are close to this side. So let's do our carbon, chlorines. So you can see this is kind of a pain in the butt drawing all this. That's why we use that generic one we'll show you in a second. So over here, we got the partial negative, partial positive, and you can see where that dipole-dipole force comes from, right? And it's the same electrostatic attraction as a cation with an anion. It's just not as strong, right? So if we want to do kind of a generic look at it, where we don't identify the specific molecule, we just say a generic polar molecule, or we can represent, because that's a pain in the butt drawing over and over and over, we can just say, hey, we've got this polar molecule, right? So let's say we've got the partial positive, partial negative. So that would represent maybe the chlorine sides of CH2Cl2, and this would represent the hydrogen side. If another one comes around, it's obviously going to spin and rotate so that the opposite charge side will line up, and you have the electrostatic attraction. That's a lot easier to draw than that, right? Big time. And then it can line up over, I'm not going to keep drawing those, but this could line up in 3 dimensions, right? Where you keep going. And we can draw all our fun little partial positives and negatives, right? So if we flip this up, do a partial positive, partial negative there, partial negative, partial positive there. You can see how you're going to get all these attractions moving in 3 dimensions, right? I'm not going to get into it there, but you get the idea, right? As they come together and lock into place, right? So I'm out of room on this board here, so let's look at a situation where we have 2 different polar molecules, and you'll see the same type of situation. So let's take the CH2Cl2 and the PBr3 and look at, well, how those could interact with each other. All right. I've got my molecules. Did you do it? Did you draw it? Take your CH2Cl2 and your PBr3, which we know are polar, right? Polar molecules. Even though they're different, the partial negative of one side is going to line up with the partial positive. So there's actually 2 ways you could do it, depending how you rotate the molecules, right? Do you do it this way? Do you do it that way? They're both correct. Now, one thing to point out, since these are the same electrostatic force of attraction as ion-ion, but since they're not as strong, they're going to have weaker energies, right? So the energetics of intermolecular forces between 2 polar molecules, much weaker than the ion-ion. Remember, ion-ion was like 400, a couple thousand, something like that. So huge, right? That's up there with like covalent bonds and things like that. So that's why intramolecular bonds, covalent bonds and the ionic bonds, are much stronger than intermolecular forces. We can't even call them bonds per se. They're just these weaker electrostatic forces. So when you heat up something, right, you tend to break the intermolecular forces to separate the molecules, but you're not breaking the bonds. Big difference there. So that's why you can vaporize water and go from a liquid to a vapor, right? It takes energy, right, based on the molar enthalpy of vaporization. But, heating up a pot of water, yeah, you might convert it from a liquid to a gas, but you're not going to like atomize it and separate the hydrogen from the oxygen. There's not enough thermal energy from your stove to do that. So much, much less. Okay, so I figured that was obvious, but I'd throw that on there anyway. So let's take a CH2Cl. Let's do the CH2Cl2. Draw these in real time. You can follow with me. Let's flip it around. Let's put the hydrogens here. For kicks and giggles, right? Just, it's no different than, you do this versus that, right? You can rotate it any way you want. So I have it written this way right now with the chlorines over here on the right-hand side. So I'm going to get my partial negative there, partial positive there, permanent dipole. And we did it with another CH2Cl2, but let's do it with a PBr3, where these bromines are more electronegative, and you got this negative charge by the bromines. So if I've got my CH2Cl2 like this, and I bring in a PBr3, the negative bromines are going to be attracted to the positive side here with the hydrogens. So as it's rotating around, it's going to be like, nope, nope, yep, how warm, hot, cold, boom, there we go. And if I did it the other way, it would line up this way. The positive side of the PBr3 would line up with the negative side by the chlorines, or the negative side of the PBr3 lines up with the positive side of the CH2Cl2. So it's going to lock in. It's going to be like, raw, like a docking ship. I feel like I'm playing with toys, right? And boom, and they can lock into place. Maybe not as efficiently as the CH2Cl2 with the other CH2Cl2, but you're going to see later, when we look at solubilities, what's the forces between the solvent and the solute? Right? Does the solvent like to be with itself more than the solute, or would it rather be with the solute? Right? You can see how that maybe would dissolve things more. So let's take the PBr3, and And we got, oh, I got this backwards. I have 2 partial negatives. That makes no sense whatsoever. There, that was bugging some of you, wasn't it? So I'm going to rotate my PBr3 so that the bromines are maximizing the attraction over here. So I'm going to take my phosphorus, put my lone pair there, and I'm like kind of twisting my body around. So that you can see how this maximizes up. So that central area of those bromines where it's negative rotates, and you get your dipole-dipole force. Yay! All right. So let's take a look now that you can do this. And again, you could draw that generically, right? You could say this represents the CH2Cl2 with a partial negative, partial positive. And then you could say that this represents the PBr3 with the partial negative here, partial positive there, and just draw your dashed line. Remember, we use solid lines to represent intramolecular bonds like covalent bonds and stuff. We use the dashed line to represent the intermolecular forces. They're kind of weaker. Right? So let's look at what if we take a polar molecule, right, with a permanent dipole, molecular dipole moment, and then bring that next to a nonpolar species. What happens? Very similar to the ion nonpolar species. So we have the ion-induced dipole. We're going to get the dipole-induced dipole. All right, you ready? So now we've got dipole-induced dipole. It's actually, I think, our 5th one overall. We had ion-ion, ion-dipole, ion-induced dipole, dipole-dipole, and now we've got dipole-induced dipole. I'm just breaking them up into ionic forces, dipole forces, and then what we call dispersion forces, whatever everything's nonpolar, right? So, of course, this is, you have a polar molecule with a permanent molecular dipole moment, right? And that gets close to a nonpolar molecule with a symmetric electron charge distribution. So what happens is you bring that polar molecule next to something nonpolar. For example, say this could represent, oxygen or something like that, right? So remember, the double bond is you got the sigma bond and the pi bond and all that fun stuff. So if this is completely symmetric and I bring something polar next to it, induction occurs. Remember induction, where it's going to distort the electron cloud? Now that's going to be a lot weaker than a dipole. Not a lot, but weaker than dipole-dipole. If you have 2 permanently polar molecules, those electrostatic attractions are going to be stronger than if only one of them is polar, right? So this drops down to about, 2 to 10. There's a range there, 2 to 10 kilojoules per mole, depending on how polar the polar molecule is or how strong its molecular dipole moment. How many divides is it, right? And then also how remember the factors, how large a molecule is, right? It's more polarizable. So if you're looking at the nonpolar species, the bigger it is, the bigger its electron cloud, the easier it is to distort that. Take it from symmetric to stretch it out so it has a partial negative, partial positive side. The bigger it is, the stronger that force is. So that's why you get a range going on. It depends how big the nonpolar species is and how polar the polar species is, right? There's a lot to it, right? That's why we like computer software to do it for us. Yay! So we're not doing quantitative work here, just qualitative. For example, right? Let's do it generically. I'm not going to do something specific at this point. Let's say I've got a polar species. Sound effects optional. And let's say it's got a partial positive and partial negative. So we'll call this our polar molecule. Couldn't be an atom, right? You can't have you can't have an atom with a permanent dipole, right? So that'll be some molecule. Now for the nonpolar species, that could be an atom or a molecule. Argon atoms, diatomic molecules, methane, all the hydrocarbons, things like that. So let's represent the nonpolar species as a sphere. So that's that symmetric charge distribution. We'll call this our nonpolar species. And just like we did with the ion, right, we had the cation or anion here, and it caused induction on the nonpolar species, meaning it distorts its electron cloud, right? So if this comes close to this, as that approaches it, right, Coming in for a landing. Once it gets, remember, these are short-range forces. Once it gets close enough, the electron cloud of the nonpolar species senses the electron cloud of the polar species, but it senses the asymmetry. So what do you think the electrons on this side of the polar species, even though it's symmetric, how are they gonna be feeling when this negative side, and if we rotate it around the positive side, you can see the effect, they're gonna be like, if it's negative, they're gonna be feeling, oh, get away, go, right? So they're gonna be jumping over this way going, yuck, right? That's that induction process. That's why it's called induced, right? It induces a dipole. So as that approaches, this negative side pushes electrons. Now, if we flipped this, and at the positive side here, it would pull the electrons this way. And it's going to distort that electron cloud. So now you've got the polar species. Right? So here's our polar species. With a permanent dipole. That has a permanent dipole, right? But we just distorted the cloud on this nonpolar species, and we're pushing electrons to the other side. And that induces a dipole. So we'll put an induced dipole here. So that nonpolar symmetric species, the symmetric charge distribution becomes asymmetric, and then now you can see you get this attractive force. And that's your dipole, induced dipole attraction. Oh, all right, much weaker forces. Let's look at something specific. I'm out of room. I got to erase my board. All right, let's look at an example that may have some application to your everyday life, right? So nonpolar molecules dissolving in water. Water, of course, is polar, right? We talked about that. It's bent. So if we draw that water up here, let's see, we got water like this. Right, and you got the sort of a Vesper structure, like a rotated Vesper structure there. But you've got the partial negative here, partial positive there. So that's the polar molecule. And now let's say, for example, oxygen. Right? So let's do water plus oxygen. Now, we know you've learned before that like dissolves like. That's a general rule for solubility. Solvents will dissolve more readily solutes with similar intermolecular forces, right? So a polar solvent like water is going to more readily dissolve polar solutes, right? Not a nonpolar one. So a nonpolar solute, like grease and things like that, you see oil spills where the oil just sits on top of the water because the oil's nonpolar and the water's polar. And then the oil's less dense, so it floats on top of the more dense water, and you just get this oil slick that just spreads across, right? They don't intermix there's a little bit of intermixing, right? Because of these forces, right? The water can induce a dipole on some of the oil molecules, but not much, very, very low solubility. But if that was a polar solute, it would dissolve into the ocean and bye-bye, right? You dump a bunch of sodium chloride in there, shoo, and dissolves away, right? Polar loves polar, right? So much fun. I'm going to do a whole video just on that. So if I got the polar water, you'd think oxygen, which is perfectly non-polar, right? So let's just draw O2 here. Oh, water's blue. Let's make it blue. So if I've got oxygen, with its double bond, that's non-polar. So let's say you got some O2 in the gas phase, lots of it, like 21%, right, in the atmosphere sitting over an ocean or over a lake or something like that. Grew up in Minnesota with lots of lakes. That's non-polar, this is polar, but see, that has a symmetric electron distribution. It's going to sense, if it goes into water, not much, There's not a lot of oxygen dissolved in like a lake, but there's enough for like fishies to survive, right? Or if I go down there and start breathing water, it's not going to be pleasant. I'm not going to die immediately. There's a little bit of oxygen in there, but not much for my brain to last more than a minute or two, right? I think if you've ever done that, been there, done that, it's unpleasant. It takes time to drown. So what's going to happen is you're going to see that induction occur. Right? That partial side of the water is going to push the electrons over, and so you can actually get that interaction, which creates a partial positive here, partial negative there. I'm not going to draw the whole process in there. But you've got that dipole-induced dipole. That allows nonpolar solutes to dissolve in water or any polar solvent to a small extent, right? So it dissolves to a small extent. And I'll write this again that you probably had in introductory chemistry, since like dissolves like, right? So a polar solvent is not going to dissolve a lot of nonpolar solute, but it will a little bit, enough to allow fish to live, right? They got whatever. I'm not a biology person, but they can extract enough of that oxygen out of that water, even though there's not that much, not enough for a human to survive for very long, but fish apparently can. So go talk to your biology instructor on how it does that. I don't know, right? But neat process. And that's why you get nitrogen and oxygen. And this happens in our chemistry lab sometimes. We're going to talk later about the effect of temperature on that, right? The warmer it is, it disrupts these. So if we increase the temperature, it disrupts those forces, and the gases tend to come out, right, of solution. So if you heat up water, you start to see, and you're not boiling it, you'll still see bubbles. So that's dissolved oxygen and nitrogen leaving, right? Because you're heating it up and disrupting these dipole-induced dipole forces. Sometimes that happens in our lab when people get fresh deionized water that's kind of colder out of the tap and put them in their burettes, which are room temperature. And so that fresh DI water, which has some dissolved gases in there from oxygen and nitrogen in the air a little bit, but they put it in that constrained burette and it starts warming up. You start to see hundreds and hundreds of tiny little bubbles in there. That's because the thermal motion from the room temperature is warming up the DI water with some dissolved oxygen and nitrogen, breaking these dipole-induced dipole forces, getting all those little bubbles, which can cause volume errors. That's why you want your water to be room temperature if you're doing like density experiments and whatnot. Cool stuff, right? So there's a specific example for you. So enough for this video. Let's do now. There's a third type of dipole-dipole force, but it's an extreme case that makes it very, very, very strong, way stronger energetically than you would think for just the electrostatic dipole-dipole forces, and actually pushes it in stronger than dipole-dipole, not as strong as ion-ion, but up there, and it's called hydrogen bonding, which is just a special type of dipole-dipole force based on the things we talked about: distance, polarity, size, all those kinds of things. So I'm going to do a whole separate video just for hydrogen bonding. All right, guys?